Assalamu alaikum. This is lecture number 14 of power distribution systems. So this lecture is in continuation of the previous lecture. So let's have a quick recap of the previous lecture. Over there we studied 4 feeder configuration and 6 feeder configuration. So here are some of the results of 4 feeder configuration, and these are the results of 6 feeder configuration. That is the total area served by this configuration, total load served by this configuration, percentage voltage drop in main feeder, and current of one feeder in 6 feeder configuration. And we also analyze the both configurations based on two assumptions, or we can say two cases. Those cases were thermally limited and voltage drop limited feeders. So if the feeders are thermally limited, means if the current carrying capacity of both feeders is identical, then the total area served by 6 feeder configuration is this, that is 1.5 times of the total area served by 4 feeder configuration. And if we impose the restriction on both feeders, means feeder of 4 feeder configuration and feeder of 6 feeder configuration, that the percentage voltage drop should be same, then in that case the total area served by 6 feeder configuration will be 1.25 times of TA4. Definitely the total area served by 6 feeder configuration will be higher as compared to 4 feeder configuration. The reason is that we are having 6 feeders in that case. But over here you can see that the same configuration is providing power to much load, or we can say this is 1.5 times of the 4 feeder configuration, and over here this is 1.25 times of the 4 feeder configuration. Based on this you can select the appropriate configuration. In today's lecture we are going to derive the value of K constant. So in the previous lecture we have seen that K is basically the percentage voltage drop per kVA mile, and we have also seen the graph of the K constant, and K is the function of conductor size, spacing, cos theta, and the voltage. So let's see the derivation of K constant. For that, let's consider the feeder. So this is the sending end voltage, this is the receiving end voltage, this is the length of the feeder. Suppose that the angle of sending end voltage is delta and receiving end voltage is the reference. So that's why the angle of receiving end voltage is 0. Let's consider the load connected at receiving end. So we can represent the load as P plus JQ. You must have seen this representation of the load in the previous course of power systems. So this positive sign indicates that the load is lagging in nature. This is the resistance of the feeder and this is the reactance of the feeder. So the overall resistance is equal to the product of the resistance, that is in ohms per mile per phase, into length. So this is the reactance in ohms per mile, and when multiplied by length it will give the overall reactance in ohms. So we can have the following notation. So we are performing the per phase analysis, that's why this resistance is in ohms per mile per phase, and this is the resistance in ohms per phase, and this is the per unit length resistance. The impedance per unit length can be written as So this is the overall impedance of this feeder. So L is the total length of the feeder, whereas S is the effective length of the feeder. And we have seen previously while performing the analysis for 4 feeder and 6 feeder configuration that when the load density is increasing, then the load can be lumped at 2/3 of the total length of the feeder. So in that case 2/3 into L is the effective length of the feeder. So it means the value of effective length depends upon the nature of load density. So we are going to see different cases of load density that will give us different values of effective length, which will be in terms of the total length of the feeder. So now in order to compute the voltage drop across this feeder, as we know that K constant basically represents the percentage voltage drop, and the unit of K is percentage voltage drop per kVA miles. So that will be equal to Vs is equal to VR plus Ig. This voltage is equal to voltage drop across feeder plus receiving end voltage, given by this equation, that is equation number A. Now we can express equation A in terms of phasors. You can see we have considered the angle delta for the sending end voltage, and for receiving end voltage we have considered angle 0. So that's why we can write this. And over here I have told you that the nature of this load is lagging. That's why theta will be negative. Simply we have expressed this current in terms of phasor and this sending end voltage and receiving end voltage like this. Let's see the phasor diagram corresponding to this one. So this is the receiving end voltage, that is the reference voltage. The nature of the load is lagging, so we can represent it like this. This angle is minus theta, and in order to implement this equation, we need to add the voltage drop with receiving end voltage in order to compute the sending end voltage. So this is the receiving end voltage, this is the current. When this current is multiplied by resistance and the reactance, that will give us the overall voltage drop. The resultant of this is basically Ig. This is Vs and the angle of Vs is delta. So in a typical distribution system, the angle delta is very small and the range of angle delta is also line resistance is very small as compared to line reactance. So if we want to see what is the voltage drop, then the voltage drop will be the difference between the sending end voltage and the receiving end voltage. So if we use the assumptions over here, then we can see that this vertical component will be very small and we can approximate the voltage drop using this horizontal component only. So now let's see what is this horizontal component. So this angle is theta and this angle is 90 degrees. So this angle will also be theta and this angle will be 90 minus theta. And similarly, this angle will also be 90 minus theta. Now let's draw the perpendicular to the axis. So now the total voltage drop will be this component plus this component. So this component will be IR cos theta, as this angle is theta. So this component will be IR cos theta. So I can represent it like this. Now in order to determine this component, this angle will be 90 degree. This angle is theta. So this will be Ix sin theta. So the total horizontal component will be IR cos theta plus Ix sin theta. That is this component plus this component. The horizontal component will be IR cos theta plus Ix sin theta. That represents the total voltage drop. So we can simplify this equation. This will be VR plus IR cos theta plus Ix sin theta, and this represents the voltage drop. Now the per unit voltage drop can be written as, so this is the actual voltage drop, and if we divide this voltage drop by the base voltage, then that will give us the voltage drop in per unit. So if the receiving end voltage is considered as the base quantity, then the voltage drop in per unit can be written as, now we can replace this current in terms of apparent power and voltage. As we are performing the per phase analysis, so we will have current is equal to apparent power at receiving end divided by receiving end voltage, as this current is being drawn by the load that is connected at receiving end. So if I use this current over here, the equation will be, now I can write this R in terms of resistance per unit length, and instead of using the total length of the feeder, we can use the effective length, as effective length will depict the nature of load density as well, which we are going to discuss shortly. So you know that capital R is equal to small r into L, but instead of writing this, we are going to write it like this, because this is will be later replaced in terms of L by multiplication with a suitable factor, either 2 by 3, 1 by 2 or 1. So the selection of this factor will be according to the nature of load density. So now I can represent this per phase power in terms of 3-phase power. So this is the apparent power, that is kVA per phase. This can also be written like this, that is 3-phase power divided by 3. And we can further write it like this. So if we multiply this by 1000, that will give us the power in volt amperes, as this factor is in kVA. So we can remove the K and we can represent it like this. So this is basically in volt ampere per phase. So if I use this over here, voltage drop in per unit will be, so let's suppose if the base quantity is other than the receiving end voltage, means it is possible that we select a different base voltage. So for the sake of simplicity, we can express the equation in terms of base voltage, that will be VB into VR. Remember, this VR is due to this factor, that is when we replace current in terms of voltage and apparent power. And the second value of VR was due to this division by the base quantity. So instead of expressing it in terms of VR square, we are expressing it in terms of base quantity. So if VB is equal to VR, means if you are selecting the base voltage as the receiving end voltage, then you will have VR square in the denominator. So K is basically this factor multiplied by this factor. So if you take the product, that is equal to K. So you can write voltage drop per unit is equal to S3 phase into small s into K, and K is equal to, so this is the value of K, and we are going to see later in today's lecture that how we can compute the value of K. So let's name this as equation number X. So from equation X, K is equal to voltage drop in per unit divided by S into S3 phase, that is per unit voltage divided by kVA into miles. So for percentage voltage drop, we can multiply this by 100. Now let's discuss what will be the value of S. So S represents the effective length. Here you can see different cases in order to compute the effective length in terms of total feeder length. So if the load is lumped at the end of the feeder, means if this is the feeder and the entire load has been lumped at the end of the feeder, then in that case the effective length will be equal to the total length. And if the load is uniformly distributed across the length of the feeder, means if the load is like this, so these are different laterals with distribution transformers. So you can see load is uniformly distributed, and in that case we can say that the load can be lumped at the center point, and therefore the effective length in that case will be L by 2, or we can say that the distance of the lumped load from the feed point will be at the distance L by 2. And lastly, if the load is increasing in nature, like the case which we have discussed earlier, so this is 1, 2. Now let's see the third case. Suppose this is the feeder, this is the load, and load increases like this, means we have uniformly increasing load density. And in that case, we can assume that the load can be lumped at 2 by 3 of the total length of the feeder. So in that case, effective length will be 2 by 3 L. In this case, the effective length will be L by 2. In this case, effective length will be equal to total length. You can see the lump load is at the end of the feeder. Now we have example 4.2, and this is a very interesting example. In this example, we are supposed to compute the value of K. So first of all, we are supposed to determine the value of K using equation 4.77. Now this is basically what we just have done in the derivation. So you can see this is the value of K, and this is equation 4.77 of the book. So we have already derived this expression of K, and First of all, we are supposed to determine k using this expression, and secondly, we are supposed to determine k using the curves which we have seen in the previous lecture. So now in order to apply this equation, we are going to compute the values of this R, that is the resistance per unit length, and the reactance per unit length. So first of all, let's see how we can compute the resistance per unit length. For that, we are going to use this information, that is, this is 4 size conductor, this is the voltage level, and this is the spacing. So now I am going to use the tables from the appendix of the book. You can see using table A.1 we can figure out the value of resistance. So the value of resistance for 50 degrees Celsius and 60 Hz frequency can be seen over here. So you can see for 4 size conductor, single strand, if you want to see the value of resistance at 50 degrees Celsius and 60 Hz frequency, so this will be 1.503. You can see same as DC, so it means over here the value will be same as the DC value. So this will be 1.503. Now we are not going to use this one because this is for 25 degrees Celsius. In the statement, we are supposed to use the value of resistance for 50 degrees Celsius. So this is the value of resistance. You can see this is the value of resistance, that is 1.503. Now in the next step, we are going to determine the reactance per unit length. So that will be equal to XA plus XT. So the first term is basically the inductive reactance at 1 foot spacing, and the second term is basically the inductive reactance spacing factor. So you must have already studied this in the previous course, that is power systems. So I'm just going to use the tables in order to see what is the value of XA and what is the value of XT. So in order to see what is the value of XA, again we are going to use appendix A.1 table. So we are going to use the same row, that is for 4 size conductor, and for 60 Hz frequency, this is the value of XA, that is inductive reactance at 1 foot spacing. So this value is 0.609. So you can see this is 0.609. Now in order to determine the second quantity, that is inductive reactance spacing factor, we are going to use the table A.10. So now let's see table A.10. The size of the conductor is 4 and the spacing is 37 inches between the phase conductors. So this spacing is important as we are going to compute the inductive reactance spacing factor. That's why we are going to consider this spacing, that is 37 inches. So 37 inches is equal to 3.083 feet. So you can see this is 3 feet, and over here you can see this is the value after decimal. So it means this is for 3.0. The spacing factor is this. This is for 3.1 feet. This is for 3.2 feet. But we are supposed to compute the value for 3.083 feet. So what we can do, we can compute the slope. As we know the value of XD at 3.0 feet, that is 0.1333. So for 3.0 feet, XD is 0.1333, and at 3.1 feet, the value of XD is 0.1373. So for 3.1 feet, the value of XD is 0.1373. So taking the difference over here, that is delta X, that is 0.1, and this is delta Y. So taking this difference, that is 0.004. So we can compute the slope. Slope will be delta Y over delta X. that will be 0.04. So now we can use this slope in order to determine the value for the unknown spacing. So this is the unknown spacing. Now we can use this equation, that is y is equal to y initial plus delta y. So we know the value for 3.0 feet, which is 0.1333. In order to compute for 3.083 feet, what we are going to do, we are going to take this y initial, that is for 3.0 feet, and for remaining 0.083 feet, we are going to add the unknown y. So it means we are going to determine the y for 0.083 feet. So you can see this is 0.083 feet and we have already computed the slope. So when this slope is multiplied by this delta x, you can see this is the delta x. As 3.0 is the initial one and this is the final one, so delta x is 0.083 feet, and if we multiply that with the slope, we will have the value of delta y, which we need to add with this initial y. So this is the value of y and we need to add the value of y corresponding to 0.083 feet, and finally we will have this value of y. So for 3.083 feet, this is the spacing. So you can see over here the spacing for 37 inches is 0.1366. So you can see this is 0.1367, which is approximately the same. So next is, what is the value of theta? So in the statement you have been provided that the power factor is lagging in nature, that is 0.9. So you can compute theta using this. And next we need to see what is the value of this. So as we have discussed that the value of k has been determined using the per phase analysis, so we are going to put the value of voltage in terms of phase quantity. So this is three-phase system, so it means that the given voltage is line-to-line voltage. We can simply divide 4.16 kilovolt, that is line-to-line voltage, divided by under root 3. This will give you line to neutral voltage, which is this. So now we know all the values. You can just plug in all the values in this equation and this will be the voltage drop in per unit per kVA mile. And as I have just told you while performing the derivation for k, if you multiply this by 100, you will get the value of k in percentage voltage drop. So it means the value of k in percentage voltage drop is 0.01. So this is part A of the example, that is you have to determine k using the mathematical equation. For that, we have determined the value of resistance and the value of inductive reactance per unit length from the tables given in the appendix for the given conductor size and the spacing between phase conductors, and we have used the value of voltage as a phase quantity, and finally we have determined the value of k. Now we are going to determine the value of k using the curves. So here you can see we have seen these curves in the previous lecture. So the given conductor size is size 4. So for 4 size conductor, the given line to line voltage is 4.16 kilovolt. So it means you are going to consider this curve. This is for this voltage. And you are going to consider 4 size conductor. So this is the point of intersection. And if you see, the value of k comes out to be 0.01% voltage drop per kVA mile, which is the same as what we have determined in part A. So you can use any approach you like in order to determine the value of k. Means you can compute it using the equation and you can compute it using the curve as well. So what is the advantage of determining the value of k? That is going to be illustrated with the help of next example. Now in this example, a feeder has been shown in the figure. So this is the feeder. The length of the feeder is 1 mile and the load is connected at the end of the feeder. This is very important. You can see the lump sum load of 500 kVA with lagging power factor of 0.9 is connected at the end of the feeder. So this is the total length of the feeder. Now if I want to ask the question, what will be the effective length? Now effective length is represented by S and it is defined in terms of the total length of the feeder. So just recall what we have discussed in the derivation of K constant. If the load is lumped at the end of the feeder, then the effective length is equal to the total length of the feeder. So now in order to determine the percentage voltage drop, you can see we are supposed to determine the percent voltage drop in the main feeder. We can use this equation. So percentage voltage drop is simply defined in terms of constant K. K is percentage voltage drop per kVA miles. So it means we have to multiply it by apparent power in kVA and length in miles. So this length is effective length, as the value of effective length will be determined based upon the nature of the load density. So over here the load has been lumped at the end of the feeder, so that's why the effective length is equal to the total length of the feeder. You can see effective length is equal to the total length of the feeder, which is 1 mile. Now the value of K can be used from the previous example, that is 0.01%, which we have just determined using the mathematical expression and using the curve, and the value of apparent power is 500 kVA. You can see 500 kVA load has been connected over here. So simply use the value of apparent power, the value of effective length and the value of K, you will get the total percentage voltage drop. So this is the percentage voltage drop when the load has been lumped at the end of the feeder. In next example, the only change is that we have the different nature of load. Now load is uniformly distributed across the feeder. You can see this is the uniform distribution of the load. So for uniformly distributed load, we can say that the center of gravity will lie over here, or we can say that the load can be lumped at 1/2 of the entire feeder length. So the entire load can be lumped at this point, that is S will be equal to L/2. So this is the second case, that is for uniformly distributed load, S is equal to L/2. So again you can compute the percent voltage drop. The only change will be over here. So now instead of using 1 mile directly, we will be using 0.5 miles. Rest you can see the load is still 500 kVA. The value of K is 0.01%, which is the same. The only difference is over here. So now the percent voltage drop is 2.5%. However, in the previous case, the percent voltage drop was 5%. So it means if the load is uniformly distributed across the feeder, the percentage voltage drop reduces by 1/2 as compared to the case when load is connected, or we can say load is lumped at the end of the feeder. Now in next example, the load is increasing uniformly. So you can see this is the increasing load density. Load is not uniform, rather it is increasing. So for increasing load density, we can say that the lumped load can be considered at 2/3 of the feeder length. So 2/3 of the feeder length is this value, and now you can use this as the effective length, and the value of percentage voltage drop comes out to be 3.33%. So you can see the total load is still unchanged, the value of K is unchanged, only the effective length is being changed. So in all these three examples, the only change is in this value, that is the effective length, based upon the nature of load density. So example 4.6, you can do it yourself, but this example is just the comparison of the three cases which we have just discussed. So we have seen that the percent voltage drop in case of lumped load at the end of the feeder is highest, that is 5%, and then the percentage voltage drop for uniformly distributed load comes out to be 2.5%, and for increasing load density it comes out to be 3.33%. You can see over here it is 2.5%, and over here it is 5%. So we can say that if the load is lumped at the end of the feeder, then the voltage drop will be highest, and if the load is uniformly distributed, then the voltage drop will be least as compared to all the three cases, and the voltage drop will be intermediate if you have the increasing load density. Now we have article 4.11, that is interpretation of percent voltage drop formula. So we have 5 different cases which will be used to analyze the amount of percentage voltage drop that will occur for each case. So now using these cases, we are going to basically analyze the significance of the formula which we have derived earlier. So the 5 cases are geographic extensions, load growth, addition of new feeders, feeder reconductoring, and delta to Y grounded conversion. So before discussing the cases, let me write down the formula of percentage voltage drop. So over here you can see area is equal to square of length. For square shape this will be L square, for hexagon shape this will be L square divided by under root 3. This is length of the feeder, this is K constant, this is base voltage in kilovolts, this is basically representing the number of feeders, this D is representing load density, this is representing area served by one feeder, this represents the load served by all feeders, that's why you can see N multiplied by total load served by one feeder. So this Sn is the load served by one feeder, and it is equal to the product of load density and the area, and over here you can see this is the area served by one feeder. And lastly we have percentage voltage drop, which is equal to product of K constant, that is in percentage voltage drop per kVA miles, into load served by one feeder into length and some constant. So for increasing load density, that constant will be 2/3 and so on. So now let's consider case number 1, that is geographic extensions. So geographic extension means that we are increasing the service area. So service area basically increases as a result of geographic extensions of a city. So When surface area increases, it means that the length of the feeder is being increased. So let's assume that in order to implement the case of geographic extension, we are increasing the length of the feeder. Let's suppose we are doubling it. So you can see length of the feeder is being doubled over here. So what is the impact of this on the percentage voltage drop? We want to analyze that. So if we double the length of the feeder, we know that K is not going to be changed because that is independent of the length. Definitely voltage will also not change. We are not changing the number of feeders, so this is not going to be changed. These three are not going to be changed. We are not changing the load. That's why this D is also not going to be changed. Now what is the impact on the area? So as I have told you that area is equal to square of the length. So if length of the feeder is being doubled, it means area will become 4 times. So when area will become 4 times, let's see this load served by one feeder first. So you can see load served by one feeder is equal to product of D and area served by one feeder. So if area is becoming 4 times, then definitely load served by one feeder will also become 4 times, as D is not being changed and only area is being changed. So if S will become 4 times, and if you use this value of S over here, you will see that the total load served by all feeders will become 4 times. So now let's see what is the impact on percentage voltage drop. Now use all the modified values in this expression. You can see K is not being changed, so no impact on K. S is becoming 4 times. Length is becoming 2 times. So 4 into 2, that will be 8 times. So it means if you double the length of the feeder, the percentage voltage drop will become 8 times. So this is not the desirable, and that's why this should be the least priority. Means you should avoid increasing the feeder length. The reason is the voltage drop will become 8 times. So this is not the desirable action, and that's why we should avoid it. Now let's consider the second case, that is load growth. So what do you mean by load growth? Definitely length of the feeder will not change. The value of K will not change. The base voltage will not change. Number of feeders will not change. Load growth means you are increasing the load density. So load density will become double. When load density will become double, no impact on the area served by one feeder. The reason is area is the function of length, not the function of load density. Now let's see the load served by one feeder. So you can see the formula over here, that is D into area. Area is not being changed as a result of load growth. D will become double, so S will become double. And when S will become double, definitely the total load served by all feeders will become double, as that is equal to product of N into the load served by one feeder. So you can see that as a result of load growth, D is being changed, and due to change in D, this factor is being changed. Now let's analyze finally the percentage voltage drop. So you can see K is not being changed, S is becoming doubled, length is not being changed. So when S will become double, it means percentage voltage drop is being doubled. So as a result of load growth, percentage voltage drop is being doubled. So it means increasing the load density has a negative effect on the voltage drop, because you are increasing the load growth, that is you are increasing the load density, and correspondingly the percentage voltage drop also increases. But this increase is lesser as compared to the first case, that is geographic extensions, and in this case the percentage voltage drop was increasing 8 times. So this is the worst case. This is still not desirable as percentage voltage drop is being increased. Now the third case is addition of new feeders. So this is quite evident. When new feeders will be added, you will see the change over here. That is, the number of feeders are going to be doubled. So what is the impact of addition of new feeders? Definitely when feeders are added, then the area served by one feeder reduces. So if you recall, let's suppose this is a square shaped service area and we have, let's suppose, 4 feeders in order to serve this area. Then the area served by one feeder looks like this. Now suppose within the same square shaped service area, I have more feeders. And now you can see the area served by one feeder will reduce as compared to this case. So I can say that if this is the area served by one feeder, in the second case, this area reduces to 1/2 provided that the number of feeders are being doubled. So it means if you increase the number of feeders, the area served by one feeder reduces to 1/2. Now let's see the impact on total load. So first of all, let's see the impact on load served by each feeder. Definitely when area reduces, you can see from this formula that when area reduces to 1/2, the load served by one feeder also reduces. So Sn will become 1/2 of the original one. Now let's see the total load served. So now the number of feeders are being doubled and the load served by one feeder reduces to 1/2. So the impact on Ts will remain unchanged. As this is being doubled, this is being reduced to 1/2. So you can see Tsn remains unchanged. Now let's see the impact on percentage voltage drop. So if you see over here, K is not being changed, length is not being changed. What about load served by one feeder? That is being reduced to 1/2. You can see over here. This is being reduced to 1/2 and correspondingly percentage voltage drop is being reduced to 1/2. So therefore you can say that the addition of new feeder will help to reduce the voltage drop. So this is the desirable option. So these all are basically related to the design considerations and future expansion of the substation. Now let's consider the fourth case, that is feeder reconductoring. Feeder reconductoring means that we are increasing the size of the conductor. So now let's see what will be the impact on different parameters. For that I'm going to use the curve which we have discussed earlier. So you can see this is the curve which we have seen earlier. This represents the values of K constant. This axis represents the values of line to line voltages and these represent the conductor sizes. So you can see as the conductor size increases, the value of K decreases. So you can see for higher conductor size, the value of K is being reduced. So feeder reconductoring means that you are changing the conductor size, or we can say that the conductor is being replaced. So if the conductor size is doubled, the value of K will reduce. Reason is we have already seen it with the help of the graph that for higher conductor sizes the value of K reduces. So correspondingly you can see the value of K is becoming 1/2. So the value of K only appears in the percentage voltage drop formula and none of the other parameters. That's why all other parameters will be unchanged and the only change will be in percentage voltage drop formula. So if K is being reduced, definitely percentage voltage drop will also reduce. So it means if the conductor size is doubled, that also has a good impact on percentage voltage drop, and it helps in reducing the percentage voltage drop. So this is the desirable option. Last case is delta to Y grounded conversion. Means let's suppose if the system is delta connected, you are changing it to Y type. So we know that in delta, line voltage is equal to phase voltage, and if you change this system type to Y, then it means in order to have line to line voltage, phase voltage should be multiplied by under root 3. So it means that when delta to Y conversion is being done, the voltage will increase under root 3 times due to this, and correspondingly it will have an impact on the value of K. The reason is I'm once again going to consider the same curve. So you can see from this curve that as the voltage increases, you can see this is line to line voltage and it increases like this. So this is the higher value of voltage as compared to this voltage. So for higher values of voltage, you can observe that the value of K reduces. So it is understood that when voltage will increase, the value of K is going to be reduced. Next question is, what will be the amount of reduction in K as our voltage is being increased under root 3 times? The answer to this question is that you are going to consider this formula. So this is the formula of K, and you can see that the voltage square is appearing in the denominator. So now if I consider that the voltage is becoming under root 3 times, so it means if this is the value of K, this is becoming under root 3 times, the second voltage will also become under root 3 times, as if I consider the receiving end voltage as the base voltage. So this will give us whatever is the original value of K, that will be divided by 3, as we are having under root 3 square in the denominator. So both of these voltages are being increased under root 3 times. Correspondingly, the value of K is being reduced to 1/3. So you can see this over here that the value of K is being reduced to 1/3 as a result of delta to Y conversion. Now let's see the impact on remaining parameters. So as we have discussed in case number 4, that the impact of change in K will not appear in other parameters, rather it will only be depicted in percentage voltage drop formula. So therefore you can see all other parameters remain intact and the only change will be observed over here. So now if K is becoming 1/3 and other parameters are not being changed, then it means percentage voltage drop will become 1/3. So these are the few results which you have seen as a result of performing different strategies for load growth, for geographic extension, for addition of new feeders, and for feeder reconducting. So from design perspective and for planning perspective, these all considerations are very important, as these cases give you deep insight that what will be the reaction of the performed action. So geographic extension means length of the feeder is being doubled, correspondingly percentage voltage drop will increase 8 times. Load growth, if it increases, then D becomes double and correspondingly percentage voltage drop also becomes double. So the only favorable options are case number 3, 4 and 5. So that should be done in order to increase the capacity or in order to reduce the percentage voltage drop in the system. Now we are going to solve few examples related to the percentage voltage drop Now we have example 4.8, and in example 4.8 we have to consider a square shaped distribution substation service area as shown in figure 4.25. So this is the figure of square shaped service area, assuming substation is at center, and these are the 4 feeders emerging from the substation. So you can see over here that the substation is served by 4 3-phase 4-wire primary feeders, and the voltage level is given over here. So this 4.16 kilovolt is line to line voltage and 2.4 kilovolt is line to neutral voltage. And the feeder mains are made of either H2 American wire gauge copper or H10 ACSR conductors, means aluminum cable steel reinforced. So we have already seen that the size of the conductor will be used to see the value of K constant and also the conductor current carrying capacity. This is the spacing between phase conductors, 37 inches, and this is the load density. So you can add the word of increasing over here. So the solution is for uniformly increasing load density. So now we have to compute using the two assumptions which we have discussed earlier. First of all, we have to consider thermally loaded feeders, and then we have to consider voltage drop limited feeders. Using these two assumptions, we need to compute the substation size, the maximum load per feeder, and the spacing of the substation. Spacing of the substation means we need to compute this width. So we know that this represents the length of the feeder, this represents the length of the feeder. And since we are considering the service area served by 4 feeders, so we can use the 4 subscript, and in order to compute the substation spacing, it means this will be 2L4, means this spacing and this spacing. This is length of the feeder, this is length of the feeder, and overall this is 2L4. So this is the substation spacing. Now what is the substation size? Substation size is the total load served by the substation. So in order to compute the total load, what you should compute? You should compute first of all the load per feeder, that is S4, and then you should compute the overall load, that is number of feeders multiplied by load served by one feeder. So this will give you the substation size. Maximum load per feeder is this one. This is the substation size in kVA, and this is the spacing of the substation. As you have been provided, you need to compute both ways. That's why I have taken the sum of L4. On either way, it is going to be L4 alone. And lastly, we need to compute the total percentage voltage drop. And in the second part, the percentage voltage drop is being given to us as the feeders are voltage drop limited. Now the question is, what should be given in part A? For thermally limited feeders, the given quantity will be current, and in part B, when the feeders are voltage drop limited, the given quantity will be percentage voltage drop. So using these given quantities, we are going to compute the remaining quantities. So now let's solve this example. In part A, the given quantity is the current. Now the question is, there is no current given in the statement. So how we can compute the current? In order to compute the current, you need to see these sizes of the conductors. So you can use the appendix tables, and in appendix tables you can see the current carrying capacity of this size of the copper conductor and this size of the aluminium conductor. So that comes out to be 230 amperes. Just see the current corresponding to this size and see the current corresponding to this size, that will be 230 ampere. So now let's start the solution. So in part 1, we are going to determine the maximum load per feeder. As I have told you, the maximum load per feeder is given like this, that is the S4, and it will be in kVA, and we know that S4 can be easily computed using simple formula, that is under root 3 times V line to line into current. And this is the maximum current carrying capacity of the given conductor type. So we are taking the value of current as the given quantity. The reason is we are using this assumption that the feeders are thermally limited. So we are restricting the upper bound of the current. So this will be under 3 times. Now you can see over here, this voltage is line to neutral and this is line to line voltage. So we are supposed to use line to line voltage. Therefore this will be 4.16 kilovolt and the current is 230 amperes, and this result will be in kVA as the voltage is in kilovolts. This is the load served by one feeder. In second part, we need to determine the substation size. So substation size will be determined by the total load served by the substation, and that will be equal to N times S4. So this will be 4 into 1657.2. This gives this value. So this is the total load served by the substation, hence determining the substation size. In part 3, we need to obtain the substation spacing. For substation spacing, we have seen that we should know the length of the feeder. So now let's see how we can compute the length. So we can use this as we have determined the value of the load served by one feeder, and using this value we can obtain the length. So we know that the load served by one feeder is equal to area served by one feeder into load density. So as the area being considered is of square shape, you can see it is of square shape, therefore I can write the area served by one feeder L4 square into D. We have already seen the analysis of this in the previous lecture. So this will be L4 square will be equal to divided by, now what is the value of load density? So this is the value of load density. So you can use this value over here, and this implies that L4 is equal to 1.287 miles. So this is the feeder length. And in order to compute the substation spacing both ways, we know that this is the location of the substation and these are the feeders, that is 4 feeders. So we have determined this length, and if we double this length, we will obtain the substation spacing both ways. So this will be 2L4, which comes out to be 2.575 miles. In the last part, we need to obtain the total percent voltage drop from feed point to the end of the main. Now we are assuming the uniformly increasing load density. So you can make this correction over here. And for uniformly increasing load density, we know that the percentage voltage drop formula can be written as 2 by 3. As for uniformly increasing load density, the load can be lumped at 2 by 3rd of the feeder length. So this is the length and this is the value of K, that is in percentage voltage drop per kVA miles, and we are supposed to multiply it by total kVA served by one feeder. So this will be 2 by 3 L4 into K, and we can write S4 as D into L4 square. So this will be 2 by 3 K into D into L4 cube. So now in order to determine the percentage voltage drop, we know the value of D, that is 1000. We know the value of L4, that is 1.287 miles. Next question is, what is going to be the value of K? So in this statement you can see no value of K has been provided. So we can determine the value of K using the information that has been provided. So for conductor size, this you can see the feeders are made of either this conductor or this conductor. So you can assume any. Let's suppose I am assuming this conductor because the K constant curve has been given for the copper conductor. You can see in the adjacent figure over here. So for H2 copper size, let's see the value of K. So the voltage level is 4.16 kilovolt line to line. So now in order to see the value of K, this is the voltage level and this is the conductor size. So you can see this is the curve which I should consider. So you can see the value of K comes out to be 0.007% voltage drop per kVA mile, corresponding to this value of voltage and this size of copper conductor. So we can use this value of K, that is 0.007 over here, and the value of percentage voltage drop is 9.95%. Now let's solve the part B. So in part B, the feeders are voltage drop limited feeders. So when the feeders are voltage drop limited, it means the given quantity should be the value of percentage voltage drop. Means what is the upper bound of voltage drop which we are imposing on these feeders. In the previous part, we were imposing the upper bound for the current. So the given value of percentage voltage drop is 3%. Now let's use this value. So now we are determining the same quantities, but the sequence of steps are going to be changed. The reason is the given data is being changed. Previously we were being provided with the current. So we proceeded by calculating the load served by one feeder first, and then we computed the length. But now we are being provided with the percentage voltage drop. So using the value of percentage voltage drop, we are going to compute the length first. So now let's see how we are going to proceed. So percentage voltage drop is given as 2/3 of the length of the feeder multiplied by K multiplied by load served by the feeder. So this will be L4 into K into D into L4 square. So now we have this value as 3%. The value of K is still the same as the conductor type is not being changed. So this will be 0.007. The value of load density is 1000. So you can see we can easily determine the value of L4. So the value of L4 comes out to be 0.86 miles. So in this part you can see the first part is substation spacing both ways. So you can see we have determined L4 first, so we can take 2 L4 in order to compute the substation spacing both ways. So 2 L4 will be 1.72 miles. Now let's see the second part. In the second part, we need to compute the maximum load per feeder. So the maximum load per feeder is basically equal to S4, that is given as D into A4 square. So this will be D into L4 square. So S4 is equal to, this is 1000 and the value of L4 is 0.86 square. So this will be 739.6 kVA. So this is a load served by one feeder. In next part, we need to determine the substation size. So substation size is determined by the total load served by the substation, that is TS4, which will be equal to N times S4. So it will be equal to 4 into 739.6 kVA. This comes out to be, in the last part, we need to compute the ampere loading of the main. Now, given that the maximum voltage drop in the feeder can be 3% only. What is the ampere loading? Means how much current the feeder can carry. We need to determine that. In part A, that current was given to us. And based on that, we were computing the percentage voltage drop. Now, based on the given percentage voltage drop, we are computing the current. So, in order to compute the current, we can use the simple formula, that is apparent power is equal to √3 times V line to line into current. So, we know the value of S4, that is 739.6 kVA, which we have determined over here. You can see this is the value. Line to line voltage is 4.16. So the current comes out to be 102.64 amperes. In order to convert this current in per unit, you can divide this current by the maximum current carrying capacity of the given conductor. So the maximum current carrying capacity of the given conductor is 230 amperes. So you can divide this current by the maximum capacity in order to determine the per unit current. So this completes the example 4.8.